n log n. The harmonic series diverges, but the sum of the reciprocals of the squares converges. P series with P equals 2 converges, right? So this series converges. The harmonic series diverges, so this series diverges. But what's something in between, right? Where's the boundary between convergence and divergence? Well, here's an example of a series that sits in between. It's the sum n goes from 4 to infinity of 1 over n log n. Now, 1 over n log n is less than 1 over n because n times log n is bigger than n, right? A bigger denominator makes the fraction smaller. And because n squared is bigger than n log n, 1 over n squared is less than 1 over n log n. So this thing is bigger than something that converges, smaller than something that diverges, so it's really a question, right? Does this series converge or diverge? We can use Koshi condensation. So let's analyze this series using Koshi condensation. So I'll write down the condensed series. It's the sum n goes from 2 to infinity of 2 to the n times the 2 to the nth term. So the 2 to the nth term means I put a 2 to the n times log 2 to the n in the denominator. Okay, so this is the condensed series, this is the original series. Koshi condensation tells me that these two series share the same fate. They either both converge or both diverge. So it's enough to figure out what's going on with this series. Oh, and look, I've got a 2 to the n in the numerator and a 2 to the m in the denominator, so I can cancel those, and I can rewrite this as the sum n goes from 2 to infinity, just 1 over log 2 to the n. Now I can use properties of logs to simplify this. This is the sum n goes from 2 to infinity of 1 over n times log 2. That's just because log 2 to the n is n times log 2. And then, well, look at this. This is 1 over log 2 times the sum n goes from 2 to infinity of 1 over n. Oh, but this is, well, bad or really great news, depending on your attitude. This thing here is the tail of the harmonic series. So that means that the condensed series diverges. And because the condensed series diverges, this original series must also diverge. If you like integrals, you can use an integral test. Okay, so let's do this with the integral test. So I could look at this integral, the integral from 4 to infinity of 1 over x times log x dx. That's a suitable function to consider. By definition, this integral from 4 to infinity just means the limit as n approaches infinity of the integral from 4 to big N of 1 over x times log x dx. But now how do I evaluate that definite integral? Well, I happen to know this. The derivative of log of x is what? By the chain rule, this is the derivative of log, which is 1 over, evaluated at the inside, log of x, times the derivative of the inside function, which is 1 over x. Well, here I've got 1 over x times log x. Here I've got some other function. Here I've got an antiderivative for this integrand. So that's enough for me to be able to calculate this definite integral using the fundamental theorem of calculus. So this is the limit as n approaches infinity of, well, what is this? This is telling me an antiderivative, so log x, evaluated at 4 and n. And then I could plug in n and plug in 4 and take the difference. This is the limit, n goes to infinity, of log n minus log 4. Now, what is this limit? Well, it's growing very slowly, but it is in fact running off to infinity, right? By choosing n big enough, I can make log n as large as I like, and that means I can also make log n as large as I like. So this limit is in fact infinity. That means that this integral diverges. That means that the original series diverges as well. So that diverges, but maybe if we mess around with it a bit, we can make it converge. So our original question was whether or not this series converged or diverged. And now we've seen, both by using condensation and the integral test, that this series diverges. But remember back to our original story, right? We were thinking of this series as somehow sitting in between these two series. But now where's the boundary between convergence and divergence, right? This series converges, these two series diverge. So let me try to fit another series in between these two series. Here's an example. It's the sum n goes from 4 to infinity of 1 over n times log n, and that log n is squared. Does that series converge or diverge? We can use condensation. So let's write down the condensed series. In this case, this is the sum n goes from 2 to infinity of 2 to the n times the 2 to the nth term. So 2 to the n times log 2 to the n squared. Now, how do I evaluate this series, right? If I can determine the convergence of this series, I've determined the convergence of the original series. Good news, this 2 to the n and this 2 to the n cancel. So now I'm left with the sum n goes from 2 to infinity of 1 over log 2 to the n squared. What else can I do there? Ooh, I can use properties of logs again. So this is the sum n goes from 2 to infinity of 1 over n times log 2 squared. Now I could factor out the 1 over log 2 squared. So this is 1 over log 2 squared times the sum n goes from 2 to infinity of 1 over n squared. This is really great, right? Because what do I know? This is a p series with p equals 2. This series converges. Well, that means that this condensed series converges. That means the original series converges. So we've got a convergent series and a divergent series. It's worth comparing these two series. So this series, which we're asking about, we now know converges by Koshi condensation. And we've already seen a little while ago that this series diverges. So again, we could try to play the same game. Is there something that we could try to fit in between these two? Well, here's a question. Does this series, sort of fits in between these two series, does this series converge or diverge? This is the series n goes from 4 to infinity of 1 over n times log n times log n. Well, I'll leave it to you to analyze this series.